The topic of this session is Cauchy Mean Value Theorem. Let us see the statement of Cauchy Mean Value Theorem. It says that if function f comma g from closed interval ab to r was continuous in closed interval a comma b, differentiable in open interval a comma b, and also g dash x is not equal to 0 or all x belongs to ab, that is derivative of g at any point x is not equal to 0 for all x belongs to AB, then there is a point C belongs to open interval AB such that FB minus FA upon GB minus GA is equal to F dash C upon G dash C. Now let us see the proof. This is the first proof. First, note that GB is not equal to GA. Otherwise, G satisfies conditions, all conditions of Rolle's theorem. So there exists a point C belongs to AB according to Rolle's theorem such that G dash C is equal to 0. But this is the contradiction to our assumption that G dash X is not equal to 0 or all X belongs to open interval AB. Now consider the function phi defined on closed interval AB by phi x is equal to FB minus FA upon GB minus GA into GX minus GA minus FX minus FA. Now from the definition of phi, it is clear that phi is continuous in closed interval AB because f and g functions are continuous on closed interval AB. Phi dash x, that is derivative of this, is given by FB minus FA upon GB minus GA. From this we are calculating g dash x minus f dash x, which implies that phi is differentiable in open interval AB because g dash x exists, f dash x exists. And third, phi a, when we calculate, if we put x is equal to a, we get 0. And phi b, if we put x is equal to b in this expression, we get 0. That is phi a is equal to phi b. That is, phi satisfies all conditions of Rolle's theorem. Hence, there exists a point C belongs to open interval AB such that phi dash C is equal to 0. But this implies by putting the value x is equal to C in phi dash x, we get FB minus FA upon GB minus GA is equal into G dash C minus F dash C is equal to 0, which gives FB minus FA upon GB minus GA is equal to F dash C upon G dash C. Hence the proof. Now let us see the second proof. Consider the function phi defined on AB by phi x is equal to fx minus a into gx, where capital A is constant to be determined such that phi b is equal to phi a. That is, the value of phi at b is same as value of phi at a. Now phi b is equal to phi a implies, by putting the value x is equal to b over here, fb minus a into gb is equal to fa minus a into ga, which gives fb minus fa is equal to a into gb minus a into ga, which on solving gives capital A is equal to fb minus fa upon gb minus ga. Now from the definition of phi, that is phi x is equal to fx minus a into gx, it is clear that phi is continuous in closed interval AB. Phi dash x, that is f dash x minus a into g dash x, as f dash x exists and g dash x exists in open interval AB. So phi is differentiable in open interval AB, and phi b is equal to phi a. That is, phi satisfies all conditions of Rolle's theorem. Hence, there exists a point C belongs to AB by Rolle's theorem such that phi dash C is equal to 0. Now phi dash c is equal to 0 implies f dash c minus a into g dash c is equal to 0 by putting x is equal to c in this expression, which gives f dash c is equal to a into g dash c, from which we obtain f dash c upon g dash c is equal to value of a, which is given by fb minus fa upon gb minus ga. Hence the proof. Now let us see the one example. Verify Cauchy mean value theorem for the functions fx is equal to root x and gx is equal to 1 upon root x in closed interval ab. Also show that the point C is geometric mean of A and B. So let us see the solution. By Cauchy mean value theorem, we have to find a C belongs to open interval AB such that FB minus FA upon GB minus GA is equal to F dash C upon G dash C. Now we have F dash x is equal to 1 upon 2 root x and G dash x is equal to minus 1 upon 2 x to the power 3 by 2, which both are exist in open interval AB. So we get, by putting these values over here, the value of FB, that is putting x is equal to b over here, and value of FA by putting a over here. Similarly for G, we get root b minus root a upon 1 upon root b minus 1 upon root a is equal to 1 upon 2 root c by putting the value x is equal to c in this expression, and minus 1 upon 2 c to the power 3 by 2 by putting x is equal to c in this expression, which gives, on solving, root b minus root a upon 1 upon root b minus 1 upon root a is equal to 1 upon 2 root c upon 1 upon minus 1 upon 2 c to the power 3 by 2, which on further solving gives root b minus root a into root ab upon minus of root b minus root a is equal to minus c. On solving, we get c is equal to root ab. Hence, C belongs to open interval AB and the point C is geometric mean of A and B. Let us see one more example. Example number 2. Verify Cauchy mean value theorem for the functions fx is equal to e to the power x and gx is equal to e to the power minus x in closed interval AB. Also show that the point C is arithmetic mean of A and B. Let us see the solution. By Cauchy mean value theorem, we have to find a C belongs to open interval AB such that FB minus FA upon GB minus GA is equal to F dash C upon G dash C. Now we have F dash x is equal to e to the power x and G dash x is equal to minus e to the power minus x by finding the derivative of f and g. We obtain, by putting these values over here, EB minus EA upon e to the power minus b minus e to the power minus a is equal to e to the power c upon minus e to the power minus c, which gives e to the power b minus e to the power a upon 1 upon e to the power b minus 1 upon e to the power a is equal to e to the power c upon minus e to the power minus c. On solving, we obtain minus e to the power a plus b is equal to minus e to the power 2c, which implies 2c is equal to a plus b, which gives c is equal to a plus b by 2. Hence, C belongs to open interval AB and the point C is arithmetic mean of A and B. Thank you.